In this video, we'll be discussing physical and chemical reactions and how we can understand quantitative relationships. In order to understand some of the properties of matter, we have to understand some of their physical characteristics or physical properties. Physical properties are things that could be measured quantitatively or possibly described qualitatively. Some examples are the melting point, the temperature at which the solid becomes a liquid for a pure substance. Boiling points, where we have a liquid going to a gas at a particular temperature. The color of a substance, possibly the odor of some volatile substance. The density of a material, of a pure substance, is unique to that material. And then whether or not the substance exists as a solid, liquid, or gas at a particular temperature. The physical changes are important indicators of the possibility of a chemical reaction, and so we oftentimes will be making measurements associated with these changes. So, for example, if we can measure the melting point, boiling points, or possibly whether or not a compound is soluble in a certain liquid to form a solution is an important property. And then finally, we can do various physical techniques that allow us to separate mixtures. So we can use filtration to separate a solid from a liquid, or we can do chromatography to separate substances from one another, or we could possibly use distillation to separate more than two liquids from one another based upon their boiling points. Shown here is an example of a distillation, which can be used to separate a mixture of sodium chloride and water, essentially salt water. If you heat that mixture, which is in the round bottom flask on the left, you can get the water to boil, which then produces the bubbles of water vapor. The water vapor then goes up into the neck of the flask and then reaches a height where it starts to come over into the sidearm. There we have a reflux condenser where there is cold water running through the outside of the jacket. This then cools the steam, producing liquid water that drips into the receiving flask, which is the Erlenmeyer flask on the right that you see here, producing pure water. When you're done and you have transferred all of the volatile water into the Erlenmeyer flask, you have effectively separated the sodium chloride, the salt, from the water, and now you have two pure substances. In order to distinguish a chemical change from a physical change, we need to decide whether or not a reaction produces a new substance versus simply produces the same substance in a different phase, say going from, say, the solid state to the liquid phase, which would be simply the melting. So the crucial thing is that a chemical property of a substance is specifically going to involve changing a material into a new chemical formula, and oftentimes these are not reversible processes or not readily reversible processes, whereas physical changes can often be reversed pretty readily. So again, the crucial thing is we're producing new materials, and these materials have distinctly different physical properties. Some examples, if you were to take iron and react it with elemental oxygen, you would get the formation of rust. This is a so-called oxidation process. The orange rust is distinctly different than the iron or the oxygen you start with, and it's not readily possible to make that reaction go backwards. Likewise, if we were to burn gasoline, gasoline is a complicated mixture of hydrocarbons. Reacting that with elemental oxygen produces oftentimes carbon dioxide and water as a complete combustion reaction, and it is not an easy process to reverse that reaction. So these reactions must follow the law of conservation of mass, where we state that the number or the amount of mass that we start with must equal the amount of mass that we end up with in a chemical reaction. You can't create or destroy matter by doing a chemical reaction. It is possible to use a variety of words in the form of a sentence to describe chemical reactions, but more often than not, we often will take these descriptive terms and transform them into a symbolic language that chemists use to describe reactions. So, for example, we see here a chemical reaction in which the element sodium, which is a solid at room temperature, is reacted with gaseous chlorine and providing a chemical reaction that produces the compound known as sodium chloride, which happens to be a solid. As you see on the right, this is a pretty exothermic kind of reaction, producing both heat and light as a result of the transformation. The reactants are the sodium and elemental chlorine that you begin with, and these are always on the left-hand side of the reaction to the left of the arrow that you see here. The products are to the right-hand side of the arrow, and they're shown now in red. And so in this particular case, we would then talk about the so-called stoichiometric coefficients that are the numbers in front of those formulas. If we talk about this on the atomic scale, it would take 2 sodium atoms and 1 chlorine molecule, 1 Cl2 molecule, to produce 2 sodium chlorides in the solid state. Those stoichiometric coefficients can also be described in terms of moles. So in terms of taking 2 moles of sodium and 1 mole of chlorine, diatomic chlorine gas, it would produce 2 moles of sodium chloride. In addition to the chemical formulas in a reaction, we also always include phase designations. So in parentheses just to the right of each of the formulas, you would see some sort of indication of the phase of matter those substances exist in. So in terms of the 3 standard phases of matter, a parentheses with a G would represent gas, parentheses L would be liquid, parentheses S would be solid, and then in some cases, parentheses AQ, this stands for an aqueous solution, where aqueous stands for the liquid water. In addition to writing chemical reactions, we can also represent certain physical transformations. As an example of that, we see here the interaction of solid calcium fluoride with liquid water to produce a solution. Whenever an ionic compound such as calcium fluoride is dissolved in water, it always breaks apart into its component ions. So what you actually end up with in solution are calcium 2+ ions that are then separated from the 2 fluoride ions, and then also you have the water, which is acting as the solvent. This is typical reaction for any ionic compound, and we'll be doing this quite often. The overall reaction can be abbreviated somewhat because we don't need to indicate the liquid water. It's implied when we have the parentheses AQ, so this reaction can be simplified down to just simply calcium fluoride goes to form calcium ions and 2 fluoride ions. You'll notice the stoichiometric coefficient of 2 in front of the fluoride to make sure that we obey the law of conservation of mass. So, in fact, this reaction can go in both directions. It's not just a single-headed arrow, which implies it only goes from left to right. But in fact, we can have the reaction go in the other direction to some extent as well. So if we took and combined a solution of calcium ions with another solution that contains fluoride ions, we may well end up with the formation of some solid calcium fluoride. The double-headed arrow is an indication of what we refer to as an equilibrium. In addition to the information provided in the chemical equation as we've discussed so far, there is sometimes additional information. In this case, we show a chemical reaction in which two sodium nitrates in the solid phase are then heated to produce two sodium nitrites plus elemental oxygen gas. The addition of heat is indicated by the Greek letter delta, capital delta, over the top of the arrow that you see here. So this is an addition of heat in this particular case. The other kinds of information that you'll sometimes see above or possibly below the arrows could also be the addition of a possible catalyst. A catalyst is some substance that speeds up a chemical reaction. It takes part in the reaction but is neither a reactant nor a product of a chemical reaction. So for example, here we have two carbon monoxides reacting with elemental oxygen, and this is catalyzed by alloy of platinum and ruthenium to produce carbon dioxide gas. This is the reaction that could occur in a catalytic converter in your car. And it's important to get rid of the carbon monoxide gas because it is a potential toxic gas that if you were to breathe it, you could suffocate. In order to make sure that we obey the law of conservation of mass, we have to be able to balance a chemical reaction. In order to do that, we're going to use our stoichiometric coefficients to make sure that we have the same number of atoms on both sides of the arrow. And so as an example of this, a relatively simple example, we show here the reaction between elemental hydrogen and elemental oxygen in the gas phase, which, if we were to provide a spark, would produce steam or liquid water, depending upon if it had been condensed. In this case, you'll notice the stoichiometric coefficient of 2 in front of the hydrogen and the water. So to account for this, we have to count up the number of hydrogen atoms on the reactant side. So the 2 in front of the formula times the subscript 2 in the formula gives us 4 hydrogen atoms. On the product side, there are 2 hydrogens in a water molecule, and if we multiply that by the stoichiometric coefficient of 2 in front of the formula, we get 4 hydrogen atoms as well. So hydrogens are balanced in this reaction. In terms of the oxygen atoms, there are 2 oxygen atoms in the O2 formula, and there is an implied 1 as a stoichiometric coefficient in front of that formula. If we look at the product side, there is 1 oxygen atom in a water molecule, but then we multiply by the stoichiometric coefficient in front of the formula, so we have 2 oxygen atoms on the product side as well. So, in fact, then this is a balanced reaction that obeys the law of conservation of matter.